Okay, hello everybody. Sorry I haven't been active enough on Slack. I really appreciate you all helping each other out. And part of the problem is just being able to see what's going on your individual computers. So I'm going to send out a doodle poll now and ask you guys to let me know when is a good time. And then today we're going to go over some about logistic regression, and there's some lab materials for you guys to actually start doing some modeling, some with your exploratory data. And then I'll set up a Zoom link that you guys can individually queue in, and I can look at your individual issues in your environments. So we can make sure that everybody has data, has their species, etc. I will also be posting. This session should be recorded. Yeah, and I have the recording. I just need to up from last time. I'm just gonna see if I can get it into YouTube, something that's easier to see than downloading a monster video file. Yeah, let's see. So share screen. And yeah, so I will, like I said, I will be posting the video of these lectures, hopefully with YouTube or something soon today, and sending out a doodle poll to get office hours, and then making myself available. Will be the lecture and lab part will be kind of quick today to allow you guys to do it on your own time, and then I'll be working with you individually to through a Zoom link. You'll queue in. I got also a few other emails. I haven't responded to everything yet. It's been a crazy couple of days, but also I got one suggestion about maybe highlighting where it's possible, where there's like diversity and equity and justice issues along the way. And it's a big deal, and I renamed the last, oh, whoops. Oh no. Oh, I just redid this calendar and it flipped. Oh, it flipped this. The module should be up here, and then this should be down here. So this is all the deep learning module. So I reflected my reflection. Whoa, okay, little inception moment there. I'll fix that. But basically, like, I want the last two sessions that we have to be reflective about not only the machinery that we learned about in actually doing machine learning and how that works, the nuts and bolts, but then taking a bigger picture back and actually reflecting about how that shows up in society. And it's honestly, it's a little overwhelming when I really think about it, because you could, I think a reasonable argument could be made that the polarization that we've experienced in my lifetime in America and actually around the world, and the edging towards authoritarian regimes and tyranny, I mean, it could really be a big part of that could be because of the rise of AI and the feeds that are being sent to your eyeballs to grab your attention, to inflame, and inflammatory information tends to keep your eyeballs attuned. So that's all AI driven, and we'll do a deep think about this. But honestly, it's a little overwhelming to think about the nuts and bolts while thinking about these larger societal issues. So we're just going to relegate that to later, but it's about as important as it can be. And that's why I included this quote, that there's this promise of AI solving war, disease, and poverty, but it can also, rather than aspiring to the angels of our nature, can really bring out the demons, and could, I mean, honestly spell the end of civilization as we know it, if we let our tribalistic kind of evolutionary program get in the way of cooperating together like we need to. So all that aside, it's like, it's about as big a deal as it gets. But we will get there. Let's just learn how to tweak the dials and play with data. That's the fun part. That's less daunting. And then we'll take on these bigger issues. Okay, so so we left off with let's see, this might be a little funky to navigate now, but this link has also been changed to, I did this in parts. So originally I was gonna just have lab 1 be this big run-on document, but as I knit the document, it has to run all those other chunks. And so I've cordoned this off to the Explore. So now the URL actually has a -explore. And I also did some things, I tweaked this a little bit to include some of the problems that you guys were having, and some troubleshooting there. That link to the actual choosing the species was fixed. The image is in there now of a cute little sloth. And there's some bits about here. So you can go back and edit your own code. A lot of this, you know, as you guys I've noticed in the Slack channel, it's so much of doing data science. It's actually just problem solving. Fundamentally, it's problem solving. And this is, I just added this to say, like, if this file already does not already exist, or this redo flag is set to true. So then this is then the or statement in R. And this is saying, like, basically, if I haven't created this and I don't want to remake this, then go ahead and remake this, and then write it out, and then go ahead and read it in regardless. So this is, this idea is, it's like there's a famous computer scientist whose quote I shared last quarter, which was, the 2 hardest things in computer science are naming things and cache invalidation. And this is cache. So I'm caching this file and then rerunning it. But if you were, and then I do similarly look for subsequent files using this technique. But if you, for instance, changed the use of this occurrence function to expand the number of records you get, and then you want all the subsequent outputs that might use the same caching, you want to set that redo flag to true, and then it will execute those chunks. So inside the conditional if. So so here I'm just getting 500 rows. It looked like there's some issues with writing the SF. And so I'll look on your computers. Maybe it's because it wasn't a character, but a factor type column or some other list type column. And then, yeah, so this is, some people had some issues, I guess, with seeing a data table in their knitted document. So I'll look in your environments for that. And then I also was noticing that when I was knitting this and then pushing this up, previously I used this map view, which is a really quick function to plot out spatial data. So vector data is points, lines, and polygons. raster data is like the pixelated data. And the pixelated data, what it's doing is actually taking a geographic projection. So that's each, I forget the size of each, it's in terms of decimal degrees, like maybe it's a half a degree. And we live on a planet that's described based on a spherical coordinate system that is 360 degrees around, and then 180 in north to south. So that actually gets, when you use the map view, and all the like slippy maps like this I had before, the Stamen or the background maps that you might see, those are in this Mercator, web Mercator projection. So it's actually projecting those, and it can be just these big background files. So this is just a quick view to be able to spit it out and here to see that, yeah, this is global. And then what we want to do is then clip the global data to where we actually see the species. And then we're going to grab these pseudo absence points within that convex hull to then try to create a set of background points with which to differentiate. And that's the modeling part that we're going to get to today. So here's one of those other conditionals that I added. If it doesn't already exist, or I'm redoing this, then go ahead and write this raster stack out and then read it back in. Yeah, and so then this is the clipped version of that raster stack. And then we generate those pseudo absences. And then this is where we're combining where we've seen the critter and where we've generated these pseudo absences into a single data frame. And this is
can you talk more about the pseudo absences and like what exactly we're doing?
Yeah, and part of this is all just like data preparation. So it'll become more clear when we go into this next step of actually doing logistic regression. I haven't been looking at the chat too, so, okay. Yeah, so, whoa. Okay, so what we're trying to do fundamentally here with is trying to differentiate where we've seen an animal versus where we haven't seen the animal, or we might call it also background. And that's the point of generating pseudo absences, because we need to statistically define one versus the other. And that's why we're generating this. And as an example here, here's the presence. We code as, if it's an actual presence, and we code it as 1. And if it's absent, we code it as 0. So I just included the first 10 rows of this final data frame, and then the last 10. And so this gets modeled as like it's a binomial term. So you can either have presence or absence, and that's why we needed that pseudo absence, is to basically create something with which to differentiate. So we don't know, for instance, is like the temperature. This is a tropical animal, tropically occurring animal, but is that temperature, is it the range of the entire planet, or is that temperature kind of specific to its habitat? So by understanding where the absence of the background values are, we can actually say, like, here's how specialized the habitat or the niche of this animal is.
And how does it know like where to put the absence points and like how many to do? Like, for example, like it's not like every single piece of the convex hull other than the observation points are gray. Like there are pieces in this map that are like, that aren't just gray or green?
Yeah,
Kind of to jump on that question, like what is the resolution of each row or each point?
yeah. Okay, these are great questions. So there's always like the devil is in the details, and these actually have repercussions when we model. So as with everything here, you can look at the code, and like in this case, you can click on this link and look at the function where this comes from. So it generates random points to extract background values, or random absence or pseudo absence, sampled without replacement. So there's in statistics, as you guys should know, there's when you sample, you're grabbing one of, say, a list of values. And without replacement means that you're not going to grab that same value again. Otherwise, you could get a point that's stacked right on top of the other. So it's sampling without replacement. So it's going to distribute it across the area. And it's weighted by the size of the cells. So yeah. So these are the details of this sampling regime. If we actually look at, I'm trying to just provide you guys all with a unique example, so you each have a unique species to be able to play with this and see. So I did constrain it to within a reasonable study area. You know, like Sloss Meta, the evolutionary, had the chance to go over into Africa, you know. And so we do want to like constrain our study area with which we do that pseudo absence sampling somewhat. But you also notice that if you go up and look at, a lot of this is coming from this species distribution modeling with R. Here, this has a lot of this original functionality, but you'll notice that creating absence and background points. So here's their code for doing this and creating these random points. So they kind of do a few different ways. There's a few different ways of doing this with where you constrain it. One is maybe just like having this very large bounding box, maybe a smaller bounding box. Or here's another method of actually taking all the presence points and then buffering a circle around them. And then this is your mask with which you drop points within it. So the mask that we create it's intentionally excluding the pixels where we have actually seen the animal, and then but allowing us to drop those random points within a given study area of the rest of the mask. So this
Can you share that link in the chat?
Yeah, it's actually it's at the top of the
Thank you.
It's at the top of the lab as well. The general link for the species distribution modeling.
Hey, Ben, I have another question about the absence points. So for mine, based on like the size of the distribution area of my mask and like the resolution, it ended up being that there were fewer pixels in the mask than there were absence points or observations, like the number of rows. So essentially it put a point in every pixel, and so it wasn't random. So what would I do about that?
Yeah. Yeah, and the idea here also is to try to create a balanced set between the number of observations and the number of pseudo absence. So there's many ways of approaching this. You could reduce the number of observations, like randomly sample that and then do a smaller sample of pseudo absence. You could expand the area that you're sampling from, like do a buffer around that convex hole. There's an st_buffer function to be able to expand that. Or you could increase the resolution of your raster so that then there's more points from which to sample.
Okay.
Or you could create your own random sampling function that doesn't bonk when you run out of pixels. So that where it would be, maybe it's sampling with replacement, with replacement. So any and all of these things could apply. Yeah.
Okay, thank you.
Mm-hmm. So I appreciate these bigger picture questions, especially about like, wait, what was going on here? Because it was kind of a blitzkrieg at the end after doing a lot of introduction to machine learning in general. This will actually become hopefully much clearer when we now go into doing the actual modeling, and you'll see how we needed this pseudo absence to separate the environment. And I ended here last time with this term plot. So really the idea is how can we build a statistical model that separates this species' unique presence in the world based on these environmental predictors versus some background or absence where we haven't observed the animals. And that here we have presences in green and absences in gray. And this is a density histogram. So for all of our presence data, this is the density is on the x, or excuse me, each predictor's value is on the x-axis, and then the y-axis is then saying, here's how many of these observations we're seeing. So we're seeing basically for this first one, there's more of a peak in the background values in the overall study area that's higher in value, and this it's a little bit more dispersed, and there's more lower values for the sloth. So it's maybe a little bit drier than average through that study area. Longitude, you see that it prefers lower longitude versus more distributed longitude. And you can see the latitude it prefers higher latitudes versus a more distributed latitude. So with that, let's go into actually taking this data and building a model out of it, and then we'll go back and maybe open it up to more general questions, and then I'll make myself available to look at your individual machines. So unless there's any burning questions, I'll continue. Okay, so let's talk now about the simplest kind of form model with this very simple response of either present or absent. So with logistic regression, if you have a linear regression, so the response term can vary outside of this range of 0 or 1, and we'll do this in the lab. You'll have code to actually see that. And whoops. And with logistic regression, all we're doing is applying a little mathematical tweak on the response term in order to constrain that response to being either 0 or 1. And you'll notice that it's not actually, so you can get a range of values. So we're not predicting either absolutely a 0 or absolutely a 1. That's kind of what we're going to talk about next time, which is classification. So in terms of modeling, we generally have, there's regression, which can be continuous, and classification, which is categorical. It's either one value or the other. And we can have confidences of which class it is But another tweak, logistic regression, is somewhere like kind of in between, where we're actually doing regression. So we are getting a continuous response, but it's actually for just a binomial. It's for like, it's one of two categorical values available. And it's going to range between 0 and 1 to then convert it from that range of values. We can apply a threshold. We can say like, well, everything that's greater than like say 0.5, I'm going to call 1. And everything that's less than 0.5, I'm going to call 0. So the response is along this line, and the dots are the original data, the true data that is categorical. So this response, you know, it can go outside that. This is constrained within, and then we basically can apply a threshold to then convert that to either a 0 or a 1, and not a 0 to 1 decimal value. So this is how this is done. This is from the text you guys had last quarter in Tam's class, and all we're doing when we're doing regression is we're figuring out, okay, what's the intercept, right? Here's our y, basically. Here's what our response term that we're trying to predict, and it's the probability of being either a 0 or a 1 on some continuous range. And this is the logit transformation that converts that into this constrained set of values. And then we're using ordinary least squares methodology. It's trying to reduce the residuals on where that line fits through all those data points, and coming up with a coefficient that minimizes the error. So either all the b's or the betas are these individual coefficients for each of these predictor terms, and you can think of this as row by row. So the sub I is saying, like, for that individual row of data, we're going to get this that row's y back or close to it with some error. And so this is the range of values here when we apply that logit transformation. Okay, so that's how we go from a linear model to a generalized linear model, is applying this logit transformation. And you can see that here's like a GLM on this first term in my sloth example. And there's this negative correspondence. As we go bigger in altitude, it's less likely that you're going to see a sloth. And that kind of jives with that term plot that we had before. Because as we see more sloths in lower elevations, and as we, it's not a very differentiable one, but we do see more sloths in lower elevations, and versus the background has slightly higher elevations. And that's why we see that. And then what we can do, and here's the formula for doing that. So we have present is our response term. So that's that 0 or 1. And then we're predicting with the tilde in the formula this predictor term, this altitude. There's another modeling technique called a GAM, or generalized additive model, where we can add wiggles. So it's going to do a much more flexible fit on the data. And here's the term plot for that. So here we can see that it's like wiggling. There's also the error bars as we have less and less data, which is given by this, what's called a rugosity or rug at the bottom. So we see there's a lot of data points on these smaller values. And then as we increase in altitude, there's far fewer data points. And that also helps explain why we have wide error terms. So there's actually like process error, like maybe the sloths don't have a really specific altitude or fit. And then there's measurement error, like maybe we haven't actually detected all the sloths. So the couple kind of ecological kind of terms I'll share back on that too. But yeah, so now we're advancing from a very simple linear model to a generalized linear model where it's more realistic with it ranging between 0 and 1. And then now we're like adding more wiggle to the model with a generalized additive model. And then the next thing that we can do is actually use this other thing, which is probably the most commonly used species distribution modeling technique out there, which is called maxent. So this is short for maximum entropy, which is entropy is chaos, and it's kind of, it's a lot like the technical underpinnings are a little bit funky, but the basic idea is that it's just fitting a little niche, but it allows for presence only terms. So you're actually, in this case, you feed it the entire raster. And then with that raster fed in, then you are, it'll sample, the program maxent will sample the points for you, the underlying rasters, and then it'll sample the background, and then it'll build the model accordingly. So because there's so fewer, the requirements are much fewer, you actually only need to say, like, here's where I saw the species, and here's my environmental data. You don't have to prep as much data. And there's also a nice graphical user interface for it to be able to input the data, and it's in Java. This is and it also handles very few presence data points pretty well. So this is why this is actually the most commonly used technique. So you guys will use this too at the end. And in this case, we get these term plots. So each individual predictor term, we can then look at the response, and you can see from this paper, here are the term plots, and they're like a whole bunch of step and funky kind of shapes, and it just can fit funkier shapes also. And the paper that I had you guys read was interesting because it talked about ecological inference versus like predictive power. And if we just are interested in doing the best job of predicting where something is, then maybe we're okay with all these extra wiggles and funky response terms. But if we're actually interested in like understanding like what is like the ecological function, we might want to actually constrain how much each of these terms can wiggle, etc. So like when I was doing predictive modeling for whales and dolphins, you can constrain what's called, the wiggles are also called knots. And you can say like, well, only give me like up to 5 knots so that it has some ecological interpretability. So that's another aspect of this to consider, is predictive performance versus ecological kind of interpretation. Like it would be hard to ecologically justify each little niche and notch, or that the animal would even be able to interpret what those things mean. Those are probably pseudo proxies for something else going on. And then the last aspect of this panel from the figure from this paper is just understanding that where there's novelty in environments, you're gonna get out to the edges of those the data that you had available when you fit the model. And so where you have these edge effects is also where you tend to have the most error. And so it's very error prone when we're forecasting into the future. So trying to remove my jacket. It's a stray jacket. Here we go. Okay, so let's take a look at actually like doing this, because this is where it gets real. So if we go to this regress lab, so now I want to show just another plotting technique that's still in the exploratory kind of domain. Here we have, I'm just starting fresh. So grabbing the data we previously made in the last lab, and then showing that data. And then this is another helper little function. It's a GG plot, pairs plot. And what this is telling us is not only what we had before to differentiate the presence from the absence along the diagonal. So this is comparing pairs. So who all has seen, you can just raise your hand, a pairs plot before? Okay, maybe not everybody. Okay. So a pairs plot, it's a lot to take in at once, but this goes back to this, we want to understand like notions of multi-collinearity I mentioned before. So when we have many predictors, one can basically predict the other. So where is it? Talk about it. Yeah. So in this previous example, they talk about this problem. And a lot of times what you want to do is remove one of the variables that is already explained by the other. So we can, with a pairs plot, we can see how some of these environmental predictors are very similar to one another. And you can see that, for instance, here. So this topo wetness, you can just visually see that it's very similar to this other term. And when you're comparing, when you have the same predictors on the X as the Y, then you're gonna have an instance in this where they each show up. So it's actually taking advantage of the lower triangle has the scatter plot, and then the upper triangle has the correlation coefficients. So you can see that that this is correlated with the other. So ER topo wet is highly correlated with ER tri, and I could just see that visually. And ER topo wet here, and then ER tri, you can see that the flip of that the correlation is -0.9. So a correlation of 1 is perfect. So 0.9 is actually quite high, and you know that the angle of that correlation, it's negative. So that's where you probably want to pick one or the other of those variables in the end, and that's where this exploratory kind of stuff helps, is so you don't get that multi-collinearity, and you can kind of weed out duplicative predictor terms. Okay, so now let's get into the actual doing of the modeling, which is, you remember this is what I was sharing before about the overall process of splitting into training and test data sets, fitting the model, evaluating the model, and then predicting the model. But then we're just going to start simple, and I'm going to get into performance evaluation, maybe a little bit next time, and then really go into it the time after that. And so what we want to do to start for the simple stuff to work is we can, if we remove the terms we don't want, like the ID is not an actual data that we want to model on. That's just a row identifier, so we can backtrack. But and then we want to drop any values, any rows that have NAs that can muck up some of the simpler modeling techniques. And then later we can actually, we'll talk about in future sessions about how to impute, or I have a glossary here, and this is talking about impute, and that's where you fill in the data gaps by basically interpolating a value there. So we'll talk about that later, but for now we're just going to drop any NAs, and this tidyr, any row that has an NA on any column, this will drop. So I went from 1,000 to 986 rows here. And we're going to do a far simpler model. So we're just going to throw all the data at it, and then we're going to predict all the data back. And that's, we're just going to take it in baby steps, right? Because we're going to look at all these different techniques. So we understand what the original data was, and then we can predict back and then see how that compares the original response, or Y, or presence versus absence, 0 or 1. Okay, so we can model this and then fit a linear model. So this is what I was mentioning before too, where, you know, so much is in just prepping the data. Like that was a lot of work last round to just get to the point where we have the right data to then be able to feed into this one liner. So the fitting step, it's a one liner, and we fit the data, and you can do this little trick where with the formula, where this is the Y term that we're predicting is to the left of this, the tilde, and then the dot is lazy speak for just saying all the other columns are predictors. So we're predicting presence based on all the other columns in this data frame that we just prepared. And then let's spit out a summary of what that model looks like. So here's the formula and the data. That's the call to it. Here's our coefficients. So the intercept, that was we saw from the formula before. And then this is the coefficient, how much error. And then these are the ones that are significant. And then we've got a R squared of like 0.5. So not great, but for ecology, not terrible. And oh no. Oh, this is supposed to be D, not points E and V. Let me try that here. I think maybe I just didn't upload the latest. So we're at the fit linear model. D. Yeah. Okay, so if I were just to start fresh, get to that point where I left off. Okay, so now, and feel free to mute if you guys aren't speaking. So here we fit the model, we spit out the result, and now we can run the model. So the fit step used the specific modeling technique, and the predict, you'll notice actually that's a generic function, and it will do the specific things it needs to do based on the class of the object you feed it as that first argument. So in this case, it's a linear model. And what we can see here is that the range that we predict, it's below 0 and above 1. So that just goes back to that point that, you know, this linear regression it's not gonna cut it. We need to constrain that in order to make sense of it. And so that's what we're gonna do with this next step. So in the next step, that part I think is correct. So in this next step, this looks prettier. We can do a generalized linear model, and we can give it this binomial family. So that's the response is binomial. And this is the default link function, but so you could just say binomial. I included this just to make sure that you can explicitly see that we're transforming that response term and getting these coefficients. And in this case, what you see is that we get these different metrics for evaluating the model than the typical R squared. So we're going to talk about performance and evaluation later. But the main point is that the prediction ranges from 0 to 1. So that jives. And then we can look at the term plots. So this is looking at each individual term and how it responds. And these are just simple linear models, so not super interesting. And then we can, now here, we can actually add the wiggles. So this is, it's a similar setup. We're using a formula as the first argument, and then we're feeding the data, and we're using a family binomial. But in this case, what we're doing is we're adding those smooth terms to each of those inputs. And then with those smooth terms, it allows them to actually wiggle. And so you get basically a better fitting model. And then finally with the maxent, that's our last modeling technique. We're not actually, in this case, we're not actually going to use the absence that we pseudo-generated. We just needed those for the GLM, for the linear model, the GLM, and the GAM. In this case, like I said, maxent is going to sample the background. You just feed it the whole grid, and then it'll sample it and build the model inside. So I revised that previous part to save the clipped raster environmental stack. And this is then reading that back in and then grabbing it. So we can read that raster natively stores things as a .grd or gridded data. And we can read that whole stack back in and then plot it with the number of columns equal to 2. So now I can see that this is the clipped area that I had. And then we're gonna similarly, all we need is the presence only data. So we're gonna read in that presence only data. And this is maxent, like the old SP is the spatial package that's been around forever. And spatial features is the newer one that I prefer. But a lot of packages, older ones, still use this SP stuff. So anyway, all we do is feed it that stack of rasters and the presence only points. And then maxent basically takes care of the rest. So this is the fit step of building that maxent model. And then in this case, when we plot that model object, we don't get the term plots like in other times. We actually get this really neat thing that helps us understand what's the variable contribution. So this is ranking each input predictor as far as how much it contributes to the overall specialized niche differentiation of determining what is presence versus what's background. And this WC Bio 2 term, in this case, turns out to be the most important predictor. And this topo wet's the least, and I think there was, and some of the other ones dropped out altogether. So here, and then we can look at the individual term plots, and you'll notice that these have these like slightly funkier shapes. And then we can run the predict. And in this case, we can predict, we'll actually get a grid back of the prediction for every pixel over the entire landscape. And it's ranging from 0 to 1. And then we'll look, when we get into performance and evaluation, we'll look at how to then determine the cutoff to convert that 0 to 1 range into a binary of absence or presence, predicted habitat, not habitat later. So a lot of modeling terms, but you're actually doing it now. So we're actually taking data and we're actually building a model. We're actually doing machine learning at this point. Before we were just prepping, now we're doing it. So I will go back and add more explanatory text to this, but how about some bigger picture kind of questions, especially conceptually, before we go into sort of TA mode. And I should also say that I see Sam is she still with us? Yeah, she was.
I'm still here. Yeah.
Okay, cool. So Sam can also help maybe debug some of these little bugaboos with like not showing tables or we can look at your R session together. I'll share a link to my, I guess my personal Zoom or a meeting in the chat. Once I figure that out, and maybe if Sam, you know how to do that, you can also share in the chat, and then we can kind of do a breakout after we field a few basic questions. Yeah.
I have a question, Ben.
Mm-hmm.
So when we're looking at this pair plot, the G galley or whatever,
Mm-hmm.
and finding variables that are like highly correlated and taking them out, potentially would that be considered ordination that you were talking about in last class?
Yeah, these are really confusing terms, so I need to keep on revising and clarifying. So thank you for keeping on asking. No, the ordination, when we're talking about taking out terms, that's basically model development or calibration, and that's just reducing different potential for misinterpretation and overfitting. So we're going to get into a lot of these other pitfalls with modeling, but that's not ordination. And one of the things that I realized what I could do in better explaining this is to go back here, and it's almost like if we go back here and think about this fit step, when you fit the supervised, so ordination is unsupervised, and when you fit a supervised learning, you have the response term, you have the Y, you have a known Y, and you're feeding that into the fit. Whereas when you look at unsupervised, you don't have the Y. You're not, when you feed it into the model, you're not giving it a Y. It doesn't know. You don't know. So that's why it's unsupervised. So it will then try to like figure out, well, what is Y? In this case, it would be clusters. And in ordination, we don't know what the spread of different environmental variables is. And it's a little confusing to talk about until we actually start doing it. But in ordination, what essentially what it could do is it could take all these predictors and collapse them into two axes. And then you would see then each of your response terms as a point on that scatter plot of two axes. So it's a very different animal altogether.
Gotcha. Thanks.
When you say, once you do this pairs plot, when you say that you're going to take out the terms, where do you take them out of? This might be a simple question.
Yeah, great question. Yeah. So I didn't like show how to do that. And it's kind of a next step when we talk about like more evaluating models that I want to get into. But where you would do that, it's you could do it in a couple ways. One way is just to not add the term here. So you would this is explicitly including it in the formula when you, or I guess I should say up here when we actually feed it a formula, or you drop a column and use this lazier approach here. So you can still use this formula, and then in the data you would just say, like, you could pipe that to select minus and then whatever predictor column you don't want. So you just drop the column in the input data. So either way, you can basically exclude one of those redundant predictors. Good question. Okay, well, let's, we don't have actually that much time left. So let's go ahead and do a breakout and get into helper mode between Sam and I. And let's see if I can find my my personal Zoom link. So you guys can, I don't know if I can find it if I'm actually connected. I think if I go to the website, I can find it. Log in there. Okay, meetings. My personal room. And I'm gonna set the options so that I think it automatically does a waiting room. Cool. Okay, save. Okay. I turned off the passcode. So okay, here's Ben's personal room to get individual help. Okay. And then Sam, is that something that you feel comfortable sharing too, or?
I'm happy to have a room, but I don't really know anything about machine learning, so I don't know how helpful I can be. Happy to help troubleshoot like general code problems though.
Well, I think there was some,
useful.
yeah, great. Well, there's some simple stuff like not getting a table to show up, or you know, I don't think the questions I saw had anything to do with machine learning, but you can also just like, you can queue it up and you could be like, and bouncing back to me. So,
Sure.
and
I can definitely do that.
Yeah, feel free. And
Okay.
so sorry to put you on the spot, Sam, but
No, totally fine.
I was eager for your assistance, and I will stick around for another hour plus. So I know some of you might have class, but I'll keep the personal room open until 11:30, and then send out the Zoom or the Doodle link to get your feedback on a good office hours times. So cool. All right. Cool. And Sam, do you want to share your some link to connect?
Oh, just my personal Zoom. Yeah, I can do that.
Cool. Okay, so thank you for that, Sam. So be sure to copy these two links so that you can hit up Sam or I. And then I'll stop this call and hop into my personal room and hopefully see some of you there. Awesome. Thanks.
Thanks, Ben.
Thank you.